Hey guys, this is Jero Serrano and I develop a 3D game engine, and thank you for joining my Twitch channel today. I have a lot to share with you. I've been working hard on implementing an artificial intelligence system into the game engine, and what I've been doing is that every week I work on a particular uh, uh, artificial intelligence behavior that I want to add. And then I share what I learn on Twitch on Sundays. That has been working, quite nicely. And here we are. So, what did I do this week? Well, basically, what I worked on this week was to implement a behavior, a steering behavior that will avoid any collision with other entities in the game. The behavior is called collision avoidance, and I've been using this book, Artificial Intelligence, for games to help me out, to help me understand the different behaviors that I have to implement. And I have also been using this book, Real-Time Collision Detection System. Now, this is an amazing book, but the reason why I use it a lot is because aside from talking about collision detections algorithms, it also provides different uh, basic primitive tests that you will want to implement in your engine. And this week I actually used several primitive tests that help me with the avoidance collision uh, in the engine. So let me start. Let me share. What we're gonna be doing today. Let me change scenes here. So let me go to code. So what I have here is my characters. I have about six characters, six entities, astronauts, and they will be moving around the whole scene. And I have a bunch of trees here. Okay, and the whole idea is to predict any collision. Okay, the engine already has a collision detection system that deals whenever there is a collision. If there is a collision between two characters, the collision detection system produces a response to that collision, right? Will make both characters bounce off of each other. In this instance, what I want to do is avoid any collision, predict a collision from ever happening. And to do that, there are several things that you can go about. Luckily for me, since I already had the collision detection system already implemented, and I implemented in such a way that the collision system is divided into two different phases, into a broad phase and into a narrow phase. It helped me implement this artificial intelligence behavior a lot quicker and a lot easier if I hadn't done that. All right, so I think let me see. I guess what would be a good idea is for me to actually show you how the system works, and then talk about it. All right. So just before I begin, let me tell you this. The characters, the astronaut characters, I'm going to display them in the engine with a bounding box. But more specifically, as a sphere boundary volume. All right, and they will be moving around, and you're going to see it in a second. The trees here, they will be bounded by an AABB boundary volume. And the reason why I do that is because you number one, the trees, they are static, they don't move. And number two, you don't want to bound something, this type of entities with a sphere, because it's going to take too much space. Instead, what you do, you bound the whole entity within with a box, and that's what you're going to see. So basically, what you're going to see is a bunch of spheres and cubes and boxes. A cube, yeah. uh, uh, in the scene, and you're gonna see how the astronaut will prevent any collision, will avoid any collision from happening. All right. Then after that, I'm gonna go in depth of how that really works. All right. So let me bring up the engine here, and I'm gonna run it. All right, so it's loading the characters, the astronaut, and everything. And once that is ready, I'm going to start the behavior. All right, so right now the engine is showing right here. It's showing you know, the whole loading process and the whole retrieving data and stuff like that. Okay, so now I'm going to switch to my scene, and what I'm going to do, I'm going to start the whole behavior by basically moving my the character with the white suit. Okay, and if I start moving it, the other characters will move, and you see how that behavior will start. Now what you see here is that all of the characters will basically prevent from ever colliding with each other. If the character hits the tree, is, you know, it doesn't go all the way to collide with the tree at all. It simply just stays away from it. Actually, let me run that again, and hopefully we get a better sequence of events from happening. So right now I'm building the engine all over again, and let's see. It should come up any moment now. All right, let me just go back here. Boom, and there you go. All right, and you see how all of the characters basically will again prevent any collision from happening. There's a little problem, right, that I will need to fix. But overall, you can see how they do prevent, avoid any collision. They just bounce off each other before they actually get too close enough with the other characters to do an actual collision. All right, so that works, you know, and it works okay for now. There's a lot more to do, but basically the whole idea is there. And now what I want to talk to you about is I want to share with you how I do this. All right. There you go. All right, so let me bring this up. Let me hide this. I'm gonna keep Blender right there. And now here it is. So let me share with you everything. Okay, and before I do that, I want to talk to you about how the collision detection system in the engine works before I go into the whole behavior of collision avoidance. All right, so the collision detection system is basically divided into two parts. All right, the first thing that I do before before I do anything is I parse the space of the scene. So for example, let's say that my scene in the game has a bunch of these characters, these cars. The first thing that I do is I parse the scene, right, in such a way that it allows me to build a boundary volume hierarchy tree, which is what you see here. And it will basically, what it does, it will combines any entities that are close to each other. So for example, these two cars are very close to each other, so it will add them into a particular node in the tree. Then it will go into the other ones and it will realize that these three entities right here are very close to each other, so they should be part of a node. And then the algorithm goes even further and divides, right? It says, you know what, between these three entities, these two are even closer than the blue car here, so I want to split that node into two children node, and it will go on and on. So basically what I have here is a tree that hosts the particular that hosts data in such a way that it provides it tells the engine which entities are most likely to collide. And at this point is where I divide the whole engine into two sections, into two phases, the broad phase and the narrow phase. In the broad phase, right, with any node from the tree that has two entities that are most likely to collide, what I do is I do a quick test, a very quick test between two spheres. Basically, what I do is I bound the entity with a spherical boundary volume, and then I do a test. If the test is true, then those entities are sent to the narrow phase, and in the narrow phase, instead of using a spherical boundary volume, I use a convex hull, and that is where I do the GJK algorithm, which is very let's say that it takes a lot of processing power, so you want to use that as the minimum, as not as much. All right. So, and that's how I do it, right? So in the broad phase, I just do a quick test between two spherical boundary volumes, and then if it's true, I send it to the narrow phase. If those two items, if these two are not close enough to collide, then I just skip it and go to the next node in the tree. All right. So what I did is I realized, I already have these phases working for me, right? The broad phase and narrow phase. And the whole idea of the algorithm is to avoid any collision, prevent any collision. Well, if you think about it, the best way to detect any future collisions would be if you extract the data that is produced by the broad phase, broad collision phase, right? From here, number one, I can tell if there's a possible collision because of the two spheres intersecting, or if not. So why not get a pointer to this data and then use that data and use that as a parameter to our behavior? And that is exactly what I did. All right. So from the broad phase, I basically get this data and use it for my collision. And let me show you how I use it. So there's two scenarios, all right? So scenario number one, whenever the entities are bounded by a spherical boundary volume, such as the astronauts that you saw. So again, these are my spherical volumes, my spheres. And the first thing that I do, or the second thing that I do, is I compute the plane that is created when you intersect two spheres. Now, I know that some people may say, no, you don't. A plane is not created. You're right. A plane is not created. When two spheres are intersecting, what is created is actually a circle. All right. But if you think about it, that circle, right, can also be represented as a plane in a way. Number one, the distance between the two. Let me actually bring up something here. Here goes this page here. These are two spheres right here, right? Intersecting. the line segment AB, if you look at it from a 3D perspective, is actually a circle. All right. Now, if you recall, a plane to create a plane, you need the normal vector of that plane, and you need a particular point on that plane, right? So that way you can actually come up with the equation for the plane. Well, if these two spheres are colliding, we get this line segment, which is a plane basically, right? The normal of this line segment is basically the distance between the centers of the spheres, right? This vector that is created will provide us the plane, the normal vector for our plane, right? So we have a normal there. Now what we need to do is we need to compute a particular point on that line or on that circle, right? And once we have that point, well, we can create our plane, right? Again, this is showing this in this image is showing you what happens when you have like two-dimensional objects, and right now you see a line, but if you look at it from a 3D perspective, it will create a plane basically, a circle, and you can go a step further and visualize that as a plane. So that's what I have here in the intersection plane, right? All right, so well, why would you even use that? Well, here's the trick. What I do is I know the velocity of my entity, right? I know the direction of that velocity. Well, what I do is I create a ray in the same direction of my velocity. So I shoot the ray from my entity position towards the same direction of my velocity, and then I compute the intersection point between the ray and my plane, which is what I have here with the blue dot. This one, that's the intersection point. All right, now here's the cool stuff. I want to steer these two characters away from each other, right? So number one, I assign this point, this intersection point, as my initial position. All right, just for the heck of it, just assign as your initial position. Next, I know my plane, the normal vector of my plane, right? So I use that, and I assign a particular time parameter. You provide that, well, let's say a parameter of 2.0, all right? Well, what does that give us? Well, that gives you a new position. This is my predicted position, my initial position. Then you have a direction, right? So you have P naught. Then you have a direction, which is your plane normal, and your direction times a parameter basically gives you a predicted position, right? Which is this, my new target. So what I do, I tell my character, hey, do not steer towards your previous position that you had in mind. Steer towards the new target position. All right, and I determine that target position using my intersection point between the ray and the plane, using the normal vector of my plane, and thus creating this new position. All right, and basically, I'm sure you have seen this equation many times. You probably have seen it like this. Where is this guy? There you go, like that, right? P final is equals to P initial plus the direction of your vector times a time parameter, right? And that's how I create the target, and that's how I'm able to avoid any collision between two entities. So that's scenario number one. Now, if you notice, the trees here were bounded by a cube, an AABB cube, right? So we need to also think about that scenario. Again, in the engine also, I also implemented the collision detection system to take care of whenever there is an entity that has a special boundary volume, such as an AABB, right? So everything works the same. There's not no there was basically no modifications to the collision detection system. Or what I did, I extracted this data. So in scenario 2, we have a normal entity with a sphere volume and the second entity with an AABB boundary volume, right? Now, how it works here is a little bit different, but the whole idea is the same, all right? The first thing that we need to do is we need to compute the intersection point between my sphere and my cube. All right, now that intersection point is going to be a point on my cube that is closest to my sphere center. All right, that's the key. And I was able to determine all of that because of this amazing book. All right, the primitive test that I told you about between a sphere and a cube, a sphere and a triangle is given by this book. So that really it will help you. It helps a lot, right? So the whole idea is to determine my intersection point between the sphere and the cube and get this particular point. And here's the thing you need to remember is a point P on the cube that is closest to the sphere center. And that's it, right? Next, what do you do? Well, next we need to determine the face of the cube that this particular point lies on, right? We have a cube, right? And we know that that particular cube has 6 faces, obviously, right? You need to determine on which face that key point is on, basically which plane is that point on, right? Now to determine where that is actually quite simple. Number one, this is an AABB box, so you already have the normal vectors for each of the faces, for each of the plane. This is not the other type of boundary volume, which is a OOB, which is a little bit more complex. This one is very simple. So from the start, you already know the plane normal for each of the normal vector for each plane. And then all what you do is basically you compute the distance between the point to the particular plane that you're looking for. Obviously, most of the whenever you get an answer between the distance between the point to a particular plane to be very close to 0, then that's most likely your plane, the plane that the point is on. All right. So you compute that plane, and again, you already know by default the normal vector of that plane, right? And number 2, you already have a point, so you already have a plane basically given to you. All you need to do is look for it, look where the point is on, and then you proceed to do the same thing as before, right? You get the direction of the velocity of your entity, and then you create a particular ray, and you set the direction of that ray to be along the same direction of the velocity vector, and then you compute the intersection point between the ray and the plane, and you get the intersection point. And then what you do next is basically the whole same thing. You set this intersection point to be your original position, right? And then you get the plane normal, and depending on the particular time parameter that you give, you create your new target location, right? If you increase the time parameter, well, this is going to go all the way over here, right? So then your character will start steering to this new location. And that's it. Once you get this new target position, you basically tell the character, hey, do not don't move toward that in that direction anymore. Just steer away to the other location. And basically that's how everything works. And that's basically what I did in the engine. I actually created that new class called U for the Avoidance, and in the particular method that is in charge of steering the character, I do exactly what I showed you. Number one, I check if I should use the ABB boundary value for the particular character, and then um, do a bunch of intersection tests with the cube and the sphere, then get the plane the intersection point lies on, um, and if the particular entity is not bounded by a cube, then I just do the normal sphere to sphere test that I mentioned about, and after that, again, I compute my predicted position by getting my intersection point plus the plane normal, which is plane.n, and then a particular time parameter here, which I set it to 2. Obviously, I'm going to change this to a variable because I don't want to give it like a number. I want the user to be able to change that to whatever they want to change it to. But basically, and once I have the predicted position, I tell the character, hey, you know what, move to this new position, and that's it. That's how everything works. Again, this was a lot easier to implement because I already had the collision detection system already implemented before. So all what I had to do was to get a pointer to this data, which already had basically was already stored, was already being stored. All what I had to do is to go and get it and use it, and that's how basically it works. All right, so let's see. I hope I was able to explain that properly. Now, I want to talk to you about some stuff also. If you are a game engine developer, it is useful for you to take time to learn the tools that you will be using. And believe it or not, one of the tools that I recommend you to take some time, to invest some time on learning, is the modeling software tool that you will be using for your engine. In this case, what I use Blender 3D. This is the modeling software tool that I use. And the reason why I suggest you to take some time to learn it is because, number one, it's going to help you a lot when it comes to understanding computer graphics terminology, such as vertices, normal vectors, UV coordinates. When it comes to animations and you want to develop your animation system in your engine, it's going to help you a lot in understanding how the bone of the armature exerts a force around the vertices of your character. For example, let me see if I have. Here's my astronaut walking, and let me go to the animation here. All right, you see how the armature here is actually changing my the location of my vertices, right? It basically is deforming all of my vertices, and all of that is happening because of the bones that you see here. That is what makes making everything possible. right? Um, Understanding how that works, if not, I'm sorry, visualizing how that works will help you tremendously when you are developing the animation system for your engine. I cannot tell you, I cannot recommend this enough. Do take some time to learn this tool. You do not have to become an artist. Just take time to understand how things work. It's just gonna make life so much easier. Believe me. For example, when it comes to UV coordinates, right? If you're completely new to computer graphics, you'll be like, what is that? What is that? Why do I need to do that? Well, the UV coordinates basically are used to help the GPU uh, apply an image to your character, right? This the image that I have here is provided to your shaders, to the fragment shader, where it uses the UV coordinates to apply it to the geometry of your character, etc. So this is very useful to actually visualize it. When I started developing my engine, I was reading all of this just from a book, and they would talk about UV coordinates, but I couldn't really make sense of it until I started using Blender and really getting my hands dirty, and it really helped a lot. It helped so much. Um, the other thing why I recommend you to use this tool is because um, you know again, you don't have to be an artist, but eventually you will be buying 3D models from other marketplaces out there, such as Blender Market or cgtrader.com or turbosquid.com, etc. And many times the 3D characters that you buy, they may not be formatted properly, and whenever you try to render the character on your custom made engine, it may not work, and you'll be wasting a lot of time thinking that the problem may be your rendering engine, when it basically it's not. It's just that it was not properly set, that the character was not properly formatted to be used in your engine. Let me give you a good example. For a long time, I was having problems with characters. If whenever I wanted to scale the characters, um, something big, right, and I would render a character like this, it would fail. It would give me my game engine would give me a bunch of problems, and I was always wondering why is that happening, right? Why sometimes it works, and why if I scale something it doesn't work. Well, I realized after playing around with that tool that my scaling here needs to be set to 1. My dimensions can change, yes, like you can change the dimension, you can make something big, but the scale needs to be proportional to 1. And that's when I learned, that I have to change the rotation and make it all of it to 1. Now, as you see here, now if I render this, it will work properly, it will work just fine. Then there were times that for example, this guy was rotated in such a way like that, right? And you would think, well, the scale is 1:1. What's the problem now? Why is it rendering incorrectly? Well, then I realized that my rotation here needs to also be set in such a way that it's always 0, and that way it will the engine will properly render my character. This made me waste a lot of time, but eventually I started making sense of how things work, and now I know Blender. I'm not an expert, and believe me, I cannot do any of these 3D models at all, but I know my way around it. I know what things may what could be causing my engine to break when it comes to rendering a particular entity. So I want to share that with you. Do take some time to learn your tools. It will help you in the future. And that's about it. So I guess that's all what I had to share with you guys. I will obviously will be working more, implementing other behaviors in the engine when it comes to artificial intelligence systems, artificial intelligence steering behaviors. We'll see what I work on next. I will let you know, and hopefully I will be here next Sunday too to share that with you. Aside from that, thank you so much guys for joining, and I'll see you next time. Thank you.